All right. So Monday we started this idea of stress transformations, right? This idea that we have at any given orientation within an element, different stresses that are acting on their faces, right? And more importantly for what we're dealing with, is normally we're dealing with plane stress. We're going to be dealing with plane stress in our class. And so what does that mean? Well, that means that we get rid of all the stresses that are on the z faces of our element. And generally speaking in engineering, we assume plane stress a lot. And it's fairly accurate. Right? We usually are working with thin components that don't have a lot of out-of-plane thickness. And as we know that on the surface of our material, like the surface of this podium here, right, the normal stress is 0, okay, or the shear stress is 0. There's no stresses acting on the surface. It's always on the inside. And so we can use this assumption of plane stress. It simplifies our analysis. It makes things a lot easier, okay? So we talked about what the sign convention was for shear stress. We talked about the fact that our shear stress is acting on our 4 sides of our cube, right? This is just some small little block of material we're going to pull out. The only reason why we're looking at this little cube is it helps us look at, well, what's happening on faces that are perpendicular at any orientation, right? So if this was part of some larger bar element, like we've screwed around with in the past, right? Like this bar element, we could align that little block of material, right? It would be sitting right there, for instance. And then we could look at, well, what's happening on the surface, right? Parallel to our applied force and perpendicular to our applied force, okay? Then on top of that, we can take that little block and we can say, okay, well, if we start rotating that block, essentially starting to look at what's happening at all these possibilities of surfaces, right? In this case, we were looking at, in our example, we looked at a surface BB at a given orientation, right? So that means we essentially just rotate our block and we're going to look at what's going on, right, on the surface of our block. And we're also going to be being able to look at, well, what's happening perpendicular to that, right? So if axial member is loaded in tension, the max stress, sigma max, occurs at the face AA, right? The face that's oriented perpendicular to the applied load, right? We have this applied load P. In this case, it looks something like this, right? If we were looking at A, we had sigma X, right? Sigma Y, well, in this case, sigma Y was 0, right? We have no stresses. If we looked at a block that was oriented perpendicular, we don't get any stresses up and down, right? There's no forces in that direction. All of our forces are along the x-axis. So we got 0. Now, if we cut at an angle, right? If we remember back from our analysis when we looked at this in the axial chapter, right? If we cut at an angle, that cut then starts to experience a combination of forces, right? In order to maintain this resultant P, right? This is the resultant of 2 components, right? One that is perpendicular to the face, that would be our normal force, and then one that's parallel to the force, that's going to be our shear force, right? So if we start looking at cutting this material and surfaces in this material that are no longer perpendicular to the applied load, then we start getting both shear stresses and normal stresses, right? So if we cut at an angle, that cut experiences combination of normal and shear stress, normal and shear forces, you could say. would be our normal stress. And our shear stress, right? Sigma and tau. And from this analysis, we came up with a couple equations here, right? We said that the normal stress was equal to P over 2A times 1 plus the cosine of 2 theta, and we derived that. We also figured out what the shear stress was because of that, negative P over 2A times the sine of 2 theta. Okay. And we could plot what the stresses were doing as we changed orientation, right? We started at a 0 degree orientation. That would be a vertical plane or a plane that was perpendicular. And then as we start looking at slicing this piece of material, right, this rod, we started slicing it at different variations of theta, right? Then we start seeing this change where we start getting both a normal stress and a shear stress, right? Well, we were only looking at one surface, right? We were looking at the X face. So when we changed orientation and we looked at B, might do something like this, right? We were saying, okay, we got some sort of normal stress, sigma X. We got some sort of shear stress, right? Tau XY, right? Shear force on the X face in the Y direction. Well, we know that because of equilibrium, right? If we have shear stresses on two sides of this block, we're going to get shear stresses on the remaining two sides of the block. So we're actually going to have stuff going on a surface that is 90 degrees to that or perpendicular to that. And similarly, we might have some sigma y, right? And we would have a sigma y because if we took and we cut this material going this way, right, at 90 degrees to that, and we did another block, right, this is block B, we looked at, say, a block C. As you can imagine, we're doing the exact same thing, right? But instead of cutting it on that right-hand surface, we're going to cut it on the left-hand surface, and we're going to have shear stresses and normal stresses that are happening. And so when we look at this diagram, we really have one more stress that's happening. We have this sigma y. And so we have this relationship of the normal stresses and the shear stresses as we decide to cut our material at any angle. Okay. So where are we headed with this? Well, as I mentioned on Wednesday.
Sigma y is the inverse of sigma x, or is that just the way that it's all
It all has to do with maintaining equilibrium. So it depends on the stresses that are happening at a given point. And that's where we're going to head here with Moore's circle. So there is a relationship. They're not inverse, but they're in relationship to really a circle, and it's Moore's circle. Okay. So what is Moore's circle? Well, Moore's circle is a visual representation of the stresses that are happening at any cut plane within an element, right? At any orientation. So we could then look at, what it allows us to do is look at what's going on at any cut plane, right? We could cut this material at any given angle, and we would know what the stresses are on our faces, the X and Y faces of our cube. Which is important for us, right? Because as I mentioned on Wednesday, as engineers, we're always designing stuff for the worst case stresses, right? We want to make sure that we capture what the worst case stresses are in a material so that we can relate those back to allowable stresses, right? based on factors of safety. So we don't want to miss the maximum, which the maximum might not be where we actually calculate it, right? It'd be really easy to calculate what's going on. It's really easy to calculate what's going on a plane perpendicular, right? But that doesn't mean, in this case, we didn't have any shear stresses. But the second we started looking at a plane that's at a different orientation, we start to see shear stresses. And so if we just looked at this material and cut a plane perpendicular and said, oh, we don't have to worry about shear stresses, the normal stress is okay, right? We could miss the fact that there's shear stresses in this material and that material has an allowable shear stress, right? And that shear stress that comes of this, right, at a given orientation, a maximum where we orient this at 45 degrees, it could exceed the allowable material properties and this element could fail, right? So what does Moore's circle do? Well, it allows you to see all of the stresses, not only the maximum shear stresses, but the maximum normal stresses also. So what does it look like? Well, it's essentially a big plot. And I think next semester I'll probably give this to class because it's going to take a second here. So what do we have? We have a plot. Well, plots all have axes. Right. In this case, for Moore's circle, our axes, right? In this case, we have an x-axis and our y-axis. Well, our x-axis is positive out to the right. Our y-axis is positive downward. Okay. What do we plot on our x-axis? Well, we plot our normal stress. We plot our normal stress. So based on our sign convention for normal stress, if we plot a positive normal stress, what does that mean about that normal stress? Back to the sign convention of normal stress. Opposite. Positive normal stress is in tension, right? So anything we plot on this side we have a tension normal stress. Anything on the left-hand side is negative, right? Negative means compression. So that's on either side of our y-axis. What do you think we're going to plot on our y-axis? Shear stress, right? It's positive shear stress downward, as I said. How I remember positive shear stress? Well, positive shear stress is a counterclockwise rotation of our element. Right? So if we looked at an element up here, so this is element A. We have sigma x, sigma y, and we have shear stresses. This is going to be tau xy, or tau yx, right? Our shear stress on the y face in the x direction and the shear stress on the x face in the y direction. Right? So our shear stress is positive when we have a counterclockwise rotation. And the way I remember that is the right-hand rule, right? If we curl our fingers in the direction of an arrow, our thumb's pointing out of the page being positive. So we're going to say that we have positive shear. So anything that runs our block, right, that twists our block counterclockwise. So in this case, right, our x face shear stress that's acting here is positive, right? Our y face shear stress acting on this block is negative, right? If I'm pointing into the page. So bottom end is counterclockwise, top end is clockwise. This is negative shear. So above the line, we have clockwise. Below the line is counterclockwise. All right. Well, now that we have axes, that allows us to plot points, right? That's what we do on a plot. So in our case, what do? Well, we plot what's going on our X face and our Y face of our block, right? So up there in the right-hand corner, we've got our little block A, okay? So that block A has a normal stress and a shear stress acting on the Y face, and a normal stress and a shear stress acting on the X face, right? So we just go through and we merely plot what's going on, okay? So in our case, if we had, we're going to do this, some point there, and that would mean we're going to be somewhere like right here ish. Okay, so we've got a couple points. This could be sigma x, tau xy, right? Sigma y, tau yx, right? Those are the points that we would plot on this figure. That means also that we can create a circle from those points. Okay. Those points will have a line you can create between them, right? We know that shear stress, right, tau yx and tau xy, they're equal, right? They're equal in an opposite direction. If one's clockwise, the other one's counterclockwise. So we're always going to be equal and opposite across the x-axis. Okay. And so we can always create a line that goes between them. We're going to have equal distance above and below. All right, so this is, if we looked at this, tau yx. We're going to have some radius r. And then we'd have another component there, right? That gives us our horizontal distance, okay? So as we look on this circle, right? The x face and the y face are always going to be across the circle from one another, right? So this is a known orientation of stresses, right? These are known points due to a stress state that we calculated. We plot these points. And then as we rotate around our Mohr circle, right, we get to essentially rotate our little block A. And we're looking at what's happening at any given rotation. Right? So some points of interest to us, right, are the maximum shear stress and the maximum normal stresses. Okay? So if we look at the maximum normal stresses, we call those our principal stresses. We have sigma 1 and sigma 2, right? The maximum and minimum normal stresses. So we have sigma 1, sigma 2, what we call principal stresses. And they are the minimum and maximum normal stresses and they always occur where shear stress is 0. Right? It's always going to be along that x-axis. And if we're on the x-axis, and the y-axis being our shear stress, right? So our y-axis coordinate is going to be 0. It means our shear stress is 0. So our maximum normal stresses are always going to be on our x-axis. Okay. Well, as we can see from the circle, the maximum amplitude or magnitude of our y-axis is the top and bottom of our circle, right? Right? Tau max, whoops. Tau max. Right? They're going to be equal and opposite in direction, right? One's going to try and twist the block clockwise or counterclockwise, and one would twist the block clockwise. We could draw a line between those 2 points, right? That denotes our orientation of our block, right? What angle do we need to cut it at? Well, that angle relates back to where did we start, right? So if we started by plotting these 2 points, right? We have our y-axis stresses and our x-axis stresses. In order to move from the stress state that we calculated to our maximum shear stress, right? We would have to rotate our block clockwise and angle alpha. Right? We're going to call this angle alpha. Something that's very important here is that alpha is equal to 2 times theta, or 2 times the angle in the real world. Right? So what does Moore's circle do? Well, they take the orientation in the real world and they double it. They double it. Right? And we can see that behavior here. Right? If we started at an orientation A, and we wanted to get to our maximum shear stress, right? We would have to rotate 45 degrees. This is real world, right? 45 degrees. Well, if we, and this being our initial case was all normal stress, right? On our face and 0 shear stress. Well, if we plotted points that have all normal stress and 0 shear stress, those are principal stresses, right? So if we were to plot that original point, right? Theta equal to 0, we would be plotting our sigma 1 and sigma 2, right? These would be our points, here and here. And in order to get to our maximum shear stress, we've got to rotate 90 degrees on our Moore's circle, which is 45 degrees in the real world, right? So it just takes the real world orientation and we double it, okay? But very important, okay? So our alpha is 2 times theta. Similarly, if we wanted to, so what does that mean? Well, that means if I took that little stress block A and I wanted to get our maximum shear stresses out of it, I would take our block, right, and rotate it, that alpha, clockwise, right? And the stresses I saw, right, this point being our x faces, this would be the stress on our x face, normal stress on our x face, and the shear stress on our x face. Similarly, this would be our normal stress. Right, the normal stresses would be the same. Right, they'd be in the same direction. We're going to be on this side of the y-axis. And then our shear stresses, one's going to be counterclockwise on our y face and clockwise on our x face. Right. Similarly, if we were looking at our principal stresses and we wanted to know what orientation we needed our block to be at in order to get those stresses where we would have no shear stresses and maximum normal stresses, we would have to go either way, right? We could go this way. Where we take our coordinates and we're rotating around the circle until we get to our sigma 1 and sigma 2. And then we could rotate a block in order to get it. this point here, center, is what we call sigma average. Right? Because sigma y and sigma x are always going to be on either side of our center, right? It's just the average of the two. What else do I want to show? I think those are the main components. I think an example would help, right? So what does that mean? Well, that means we can essentially capture the behavior at any given orientation as we go around the circle. Okay? So every point on that circle is a point on each of these lines, right? If we took the x face, if we called this sigma x, we call this tau, right? Tau xy or tau yx. And then finally, if we had a sigma y, right? If we looked at any given orientation of theta, right, 0 to 180, right? Or in Mohr's circle, we're going from 0 to 360 degrees, right? We're going all the way around the circle. We're going right back where we started, from here to here, going right back to where we started. And we can look at what's going on at any given slice of our element. And ultimately, right, we want to know the peaks of this graph. We try and find the maximum normal stresses, right? Well, that happens where our shear stress is 0, right? Boom, highest normal stress, shear stress is 0. And then we have points at which we're going to get our maximum shear stress, right? Any questions? We're going to be talking about this for a while. We're going to do plenty of examples, okay? Right. There are other methods to do this, yeah.
I'm confused on like the x and y stuff, like the sigma x, sigma y, tau y, tau x, y, like.
So what do we do? Okay, so we're going to work through an example in a second. But how we generate this graph is that we're going to analyze a part. Right? We're going to analyze something just like we did with combined loading, where if we had a axial force and a shear and a torque, like on a shaft, right? That torque's going to create some sort of shear stress, and that axial load's going to create some sort of normal stress, right? And so we can develop this original block given the torque and the axial load applied, right? We're going to just develop one of these. Say, okay, if we orient a block with respect to, right, if this was a part of the overall shaft, and say we were looking at the end of the shaft, and we put a little block there, and we say, okay, I know what's going on the end. We've got a normal stress and a shear stress, right? Our normal stress in the y would go to 0 because we don't have anything, compressing that pipe, right, or shaft in perpendicular direction. So we'd have shear stress on each of our x and y faces, and we'd have a normal stress on our x face. Okay, so we established that. This block then allows us to generate our Mohr's circle, because that block essentially has coordinates attached to it, right? An x coordinate being our normal stress on the x face, right? And that normal stress on the x face has a y coordinate attached to it, which is the shear stress that's happening on the x face in y direction. So we're going to pull coordinates off of this little block that we're generating. And that's what we plot here, right? So we would plot sigma x and tau xy. Boom, we can plot it. It could be anywhere in this whole plot, right? It could be on the other side of this y-axis. The circle doesn't have to sit right here. It doesn't have to be this big, right? We're just generating it based on these two coordinates of what's going on the x face of our stress block we generated and what's happening on our y face. If sigma y was 0, right, then this point's going to be right here, right? And that point could be up there still. And then the circle would be over here. right? So based on that initial combination of how we analyze our element, right, we're gonna generate known values for stress in the normal direction and the shear direction. We can generate this plot. And from this plot, then we can figure out, okay, if we draw a circle here, where's the maximum shear stress? Where's the maximum normal stresses? And then we can relate that back to allowable stresses in the material. Yeah?
So is an X like above the sigma normal axis, or you say it can be anywhere?
It can be anywhere.
Okay.
It can be anywhere. The reason why it's right here is because on that face, our normal stress was positive, so we're on this side, and our shear stress was clockwise. So then it just puts it up there. And then our Y face, same thing, it just happened to have, right, I just put 2 points out here. It just happened to have a normal stress that was positive, so it's in tension, so it's on the right-hand side of the Y-axis. And our shear stress, it's gotta be equal, it's always gonna be equal and opposite from the other side, right? So we're gonna be the same distance down, so we get our X coordinate and our Y coordinate, they're gonna be right here. And then we draw a circle. This could be over here. That could be on this axis, or it could be, I guess, right about there. It's gotta be equal distance on either side of the X-axis. That's one thing that has to stay the same. Yes?
So it doesn't have to always go through the origin, it just happened to in this case?
Go through the origin? Oh, yeah, the circle?
Yeah.
Yes, this does, sigma 2 does not always have to be here. This circle can shift based on how much normal stress we have, right? If we have an element that's in a lot of tension, right, this might be way over here, and that circle won't even touch the origin, right? We might have a normal stress that's positive, right? The Y face might be in tension and the X face might be in compression. So we could be on either side of this axis, right? We'd still draw a circle. Yes?
Yeah, so is it always gonna be on the edge of the circle, is it gonna be inside of it, right? Or will it be-
What's gonna be on the edge of the circle?
Will there ever be like points you define inside of the circle? Or is
No.
everything gonna be everything?
Everything is on the circle. This circle is essentially taking this plot and putting it on a different plot. Okay? And it works really well because if you know 2 points, you can generate this entire graph, right? And easily calculate, just based on knowing the radius, which we'll talk about calculating, knowing the radius and where this center point is, we can figure out what's our sigma 1, what's our sigma 2, right? Our maximum normal stresses. And we can figure out our maximum shear stresses. That is the glory, that's the beauty of this thing, okay? Are there equations that do this? Yeah, where you just plug and chug and you just say, okay, I'm oriented at 33 degrees, I know what my points are, and you can just pops or principal stresses, right? But that's not as powerful as understanding, and I mean, as a practicing engineer, I have drawn more circles, okay? Yes.
So with the sigma 2 being like at the origin, like 0, that would like, I don't know, it's just confusing me that like sigma 2 would have a positive, like that would be a max.
That would be our maximum stress, which
but
would
it's
be
at
our,
0.
it's one of our principal stresses, which is, right, you're capturing our minimum and maximum normal stresses. Our maximum normal stress, in this case, with this orientation, sigma 1 is going to be way out here. It's going to be a tension value,
Okay.
right? Our minimum stress is going to be sigma 2, which just happens to be 0.
Okay.
Okay? It could be a negative value. It could be a positive value, just a smaller one than sigma 1, right?
Okay. So it just doesn't matter if it's 0.
Nope, we're just calculating a value. Yes?
Seems kind of similar like the unit circle, especially with like the sine, cosine stuff. Is there like direct correlations to them or?
No. Unfortunately, no. No, I mean, trigonometry still holds true, right? We're still gonna be calculating radiuses, we're gonna be calculating angles because we wanna know what's the orientation. Now we wanna know, okay, if we connected a bar together, right? There's going to be an orientation where we're gonna have the maximum shear stress, right? We might, as a designer, say, oh shit, we do not want to splice this at a given angle, right? Because we're going to subject however we're connecting these two pieces together, whether we're gluing them, right? fiberglassing them together, welding them together, we don't want the weld or the glue to see that maximum shear stress. So we want to glue it together at an angle that's perpendicular. Because the glue is really good at handling a normal stress, but it's not good at handling a shear stress, right? And so we can figure out what are the maximum stresses if we were to connect it at any given angle, right? Decide to cut it at any given orientation. That is best for connecting elements together, or is best for materials too, right? So, no, this is all good. We're going to be dealing with this for like 2 weeks, and the week after the break too. Okay, we're going to do a lot of examples. All right, should we start an example? First example we're going to do, we're going to look at it our initial way that we developed, right, with our equations that related our stresses based on the angle, right? Just theta. Theta is the real world orientation, right? That's this here, angle, 0 to 180. And then we're going to go and we're going to plot it and look at Moore's circle and see what it gets us, okay? So we're going to start very simple. We're going to look at this axially loaded bar, right? So it's got a axial load of 180 kilonewtons. It's 10 millimeters thick, 120 millimeters tall. And they ask us to determine what's the maximum normal stress. And then they ask us what's the normal and shear stress in an element rotated at 57 degrees, right? So this might be the case where maybe this is a metal bar and we're trying to weld it together. We have 2 pieces. Or it's 2 wood pieces and we're gluing it together in, say, a finger joint or something like that, okay? And we're first going to use chapter 1, right? Chapter 1 is the axial chapter. And then we're going to talk about Moore's circle, right? We're going to do this with Moore's circle. Well, if we look at part 1, we know from part 1, or chapter 1, right, the maximum normal stress in this material, based on the orientation of this axial load, is going to be at a section that's perpendicular, right? It takes our maximum normal force over our area. So it's as if we just were to cut this, right? Cut this plate perpendicular. We orient a block on it, right? Say it's called block 1. And we're going to look at, well, what's the stresses going on that block? So we look at that block, pull that block out, we set it right here, right? Well, we don't have any shear stresses on this block. We do have some normal force, right, acting on the x faces of this block. That's going to be our P of 180 kilonewtons, right? That's our normal force. That force is going to create a stress. We don't have any forces perpendicular to that, right? So there's no forces up here, normal. Right? There's no shear stresses. We're not trying to shear this off anywhere, right? So this would be sigma x. So our maximum normal stress is sigma x, which is P over A, which is 180 kilonewtons, which is the same as 180,000 newtons. Area is 120 millimeters times 10 millimeters. This gets us 150 newtons per millimeter squared. We all know that that's a megapascal now, so that's sigma max is 150 megapascals. And that's our maximum normal stress in our element. Part 2 is the normal and shear stress in an element rotated 57 degrees. Right? So we look at our 57 degrees. Right? We're going to essentially cut our element along that line. We're going to orient a block. Call this block 2. Right? Along that line, this being theta. So we orient a block along that line. That block So we can imagine now we're going to see the components of that resultant P force. And as we've seen before, there might be shear stresses and normal stresses. Going on in this block. Because overall, the resultant is this P of 180 kilograms, right? As we start rotating things, right, the normal stress is no longer aligned with that resultant force. So now we start creating these shear stresses, or these shear forces and normal forces like we saw up above in chapter 1, which create normal stresses and shear stresses, right? So if we look at chapter 1, they said our normal stress was P over 2A, 1 plus the cosine of 2 theta. We also said that the shear stress is negative P over 2A times the sine of 2 theta, right? All of this was chapter 1. So what does that mean? Well, we can just plug in. So this is part 2. We're looking at what's going on. Of block 2, we're going to have some sort of sigma x, sigma y, and tau xy and tau yx. Something like that, right? So if we look at sigma x, we could plug this in, 180,000 newtons over 2 times the area, which is 120 times 10 times 1 plus cosine of 2 times 57. We get sigma x equal to 44.5 megapascals. Similarly, we just plug and chug here, throw in our negative 180,000 again, all over 2 times the area, 120 times 10, times the sine of 2 times 57. Equals negative 68.5 megapascals. What does that mean? Well, that means in my orientation, it should be in the opposite direction, right? Right now, those are positive. So if we look back, we could take this off. These should be this way. Okay. A negative shear stress is on the positive face in the negative direction, right? Or a negative face in the positive direction. Or negative face in the positive direction, or the positive face in the negative direction. Right? So that would be the orientation of that shear stress. Well, we also have sigma y. Right? Sigma y is really going on, what's going on this direction. Right? Which is really oriented at 33 degrees, right? It rotated 33 degrees with respect to horizontal. So now we can do sigma y using the same equation, 180,000 divided by 2 times 120 times 10 times 1 plus the cosine of 2 theta. Now we're using 33 degrees. It's really just 90 minus, right? Our 57 gives us 33. Because we're oriented 90 degrees off from our x-axis, right? So our theta is different because our theta we're looking at is from the horizontal. So we end up with sigma y equals 105.5 megapascals. So if we created a stress block based on these values, right? Our stress in normal direction, right? Our normal stresses are positive. Right? Our force was positive, so our normal stress is positive. So we end up getting, right, outward normal. We get this shear, our normal stress in the x and y looks like that. Our shear stress we got was negative, right? So it's on the positive face in the negative direction or negative face in the positive direction. So that's our orientation. So we end up with this stress block that looks something like that, right? So that's plugging and chugging via our equations derived in the axial chapter, right? Well, we can do this with Moore's circle, okay? We can do this in Moore's circle, and we can do it fairly easily. We need our axes, right? So I'm going to put in our axes. It might run something like this. We know that our bottom is clockwise or counterclockwise, right? Positive. Curl our fingers in the direction of that rotation. It's pointing out of the page. So we're going to say tau is positive. Up here, we're going to say tau is negative. We have sigma normal is positive off to the right, right? That's our positive x direction. So it's really all we have to set up for the coordinates. From here, we're just going to plot our known value, right? And our known value was our initial stress that we calculated, right? Here. They said we've got this P force. Well, I know if I oriented a stress block that's perpendicular to that force, I know I'm going to get a normal stress, right? And no shear stresses. Right? And we know that there's going to be 0 normal stress and shear stress on our y faces, right? So our block looks something like this. Right? And we can sit there without calculating the orientation of 57 degrees. It's like, who the hell knows that, right? We would need to do some subsequent calculations. But we know that the normal stress on a plane that's perpendicular to the applied load, right? We could figure out the stresses fairly easily of what's going on in this stress block 1. So that's what we did, right? Normal stress, no shear stress, no normal stress on the y-axis. So we've established our coordinates, right? Our coordinates being the normal stress and shear stress on the x face, and the normal stress and the shear stress on the y face. So we can just take these values, and we're going to plot them on our Moore's circle. So in our case, right, we had our maximum normal stress is 150 megapascals, which is on our x face, right? So our coordinate on the x face is going to be 150, 0, right? 0 shear stress and 150 megapascals of normal stress. So we can plot this value right here. I'm going to call it 150, 0, right? It's positive, it's in tension. We're on the right-hand side of our y-axis, and we have 0 shear stress, right? We know that. There was no shear stress on that block. Similarly on the y face, right? So this is our x face. On the y face, if we look back at our block that we established, we have 0 normal stress and we have 0 shear stress. What does that mean? Well, that means we're going to sit right at the origin. We're going to sit right here. It's going to be 0, 0, right? This is our y face, initial y face. So those are our 2 points. As I mentioned before, right, we can be all over the place. We've just established of known stresses at a given orientation, right? And we're going to plot those points. So we plot those points. Now I'm going to get to draw a circle, which I really enjoy the iPad because of that. Okay, good luck. Okay, so we draw this circle. It should have sat right at the origin. It's pretty damn close. Okay. So what does this circle mean? Well, that means that we have just established what the stresses are at any given orientation of that block, right? And somewhere in here is 57 degrees, right? 2 points across from each other, 57 degrees away from our known points. And from that, we can figure out our stresses at 57 degrees, which we'll do on Friday, okay? Don't forget you have a homework due tomorrow night, right? 5 o'clock. And then you have a quiz. It started today. It's open until Friday.